So today we're going to work on the second part of Unit 1. The topic for today is Unit 1B, using variables and writing function rules. On the top of your notes page, that would go in the topic. Don't forget to put the date because that helps you put things in order. And in a minute, we'll get to our objective. While you're copying down the topic, I just want to make sure you understand this convention that I use throughout the year. You see these numbers at the end. That is your reference to the textbook. So 1-1 means Chapter 1, Section 1. 5-4 means Chapter 5, Section 4. And the ideas that we're using today can be found in those two sections of the textbook. Remember, as we go through the video, you can pause at any point in time to give yourself some thinking time or time to write or whatever you need to do. And as we go through today, it's really about introducing some vocabulary and some algebraic conventions, some standards that you're going to need to adhere to throughout the entire year. So any of the words that might seem a little new, or the notation or anything like that, I promise you we'll be using it over and over again, and it will become second nature. So our objective today is to model relationships with variables and function rules. So if you want to get that into your objective section of your notes. We're going to start with some vocabulary. And again, some of these words you've been introduced to, if not all of them. I'm just going to kind of bring them back for you. If anything seems a little bit confusing, it really will become clear the more and more we use everything. We have an entire unit later on functions. So we really, really will become experts as we go throughout the year. So the first thing, what I'm going to do, or I like to do with vocabulary, is oftentimes give you the definition and we try to figure out what the word is. As you write these words onto your notes page, you do not want to take down the definitions, just the words, so you kind of have a reference when you meet up with me in class as to what some of the words are we're using. The whole presentation will be available for you to access through Classroom, filled in, down the road, so you don't have to worry about copying definitions. All right, so backwards vocab, I'm going to give you the definition. We're looking for the word that's hiding behind that blue box. A symbol, usually a letter, that is used to represent one or more numbers, and I'm giving you some examples down here. What word is hiding back there? Did you guess it? It is a variable. And I'm giving you some examples of variables that you've been using for many years in math. T is one that science likes to use a lot. Math uses for time. X and Y are used a lot in algebra and higher math to represent sort of input and output, or the XY coordinates on a coordinate plane. So if you're plotting the point 2, 3, you might remember doing that. We'll be doing a lot of that this year. M is used a lot in algebra to represent slope, steepness of a line or a curve. And these two are a little weird over here. These are not two different variables. It is one variable. It's a special notation. We're going to get that word in a second, and I will get there in a second. All right, so the next one, a mathematical phrase that uses numbers, variables, and operation symbols. And I've given you 3 examples down here. It's not a single word. There are actually 2 words there. First of all, these are all, did you think it, expressions? And the minute you put that variable in there, it is an algebraic expression because it has that variable in there. Now, if I were to take 2 expressions, say the 2x and the 3x plus 6, and show that they were equal, in other words, put in equals in between them, no longer would we call that an expression. When we put the equals in, it becomes a or an, and that would be equation. Pretty much Algebra 1 is a lot about solving equations. Okay, so here's some more vocab words that we can put on there. This little machine that was on that first slide is showing up. If you have a relation, so 2 things are connecting, relating to each other, and you have exactly one output for each input, what is that called? Now this one I'm sure, have worked with a little bit before. I'll give you a clue. It starts with the letter F, and that might have given it away. It is called a function. I like to call this the function machine. Basically, we're going to input some value, and that would be our input variable, in this case, x. So we're going to put some number in for x. The function is going to change that, and we're going to output a different value based on the math that was done. So that is a function. An equation that describes a function, here are two right here, is called, two words, a function rule. And you might remember we saw that in our topic on the first slide. So today we're going to be talking about function rules. Let me just explain before we move on, what is this function rule? First of all, I'm noticing two variables in there. So if you notice, this guy is standing by himself out here, kind of waiting. And in here, there is a multiplication happen. I need to remind you that when you have a number in front of a variable, that what is missing, rather, is the invisible dot of multiplication. So this is 2 times x. So basically what this function rule is, what this machine would do, is we're going to put in a number for x. So we're going to take 2 times, pick a number, let's say 8. 2 times 8, and the output would be 16. So 8 would go into the function, which is to double it, to multiply it by 2, and 16 would come out of the function. So a function rule, this function rule is basically taking your input and multiplying it by 2. This function rule is taking your input and cubing it. It's multiplying it by itself 3 times. So if I was to input 2, so if I was to put 2 into this function, I'm going to raise 2 to the 3rd power, which we did in our last video, and 2 times 2 is 4, times 2 is 8, and 8 would be the output. Now, let's talk a little bit more about what this is. So you'll notice down here, this thing represents the output of a function with an input of x. You don't have to use these letters. You could use A and an N, a G and a D. So what is this stuff called? 2 words. It is called function notation. This, I'm going to pronounce for you, is not 2 variables, an f and an x. That f stands for the word function. So it's a function of x. You're kind of shouting at everybody, I've got a function rule, and the input variable is x. It's a function of x. That's what that stands for. So if we looked at, like, y, Mrs. Woodruff, why can't we just use a single variable like the y up here? Well, in algebra and higher math, we start to use this notation more. So instead of using a y, we use this. And I'm going to pronounce this for you. It's f of x, function of x, f of x. I have the exact same function rule here. Do you notice it? And this function, this machine, is going to take your input, whatever number you put in for x, it's going to double it, it's going to multiply it by 2, and add 4. I'm going to put a number in for x, I'm going to multiply it by 2 and add 4. And notice it's the same either case here. Now, what is the value of this notation? Well, you'll notice here that the x got replaced with a 5. When I replace the x by a 5, that's f of 5. I'm saying, what is the output of this function if the input is 5? So if I put 5 in for x, 2 times 5 would be 10, add 4 would be 14. So when 5 went in, 14 came out. You can see what went in, and you can see what went out. Now over here, it's the same function rule. And notice if I have the y as my final answer, I can't see what went in. I have to kind of think about it. Over here, 5 went in, 14 came out. 14 came out, So function notation has more description to it. it helps you see more of what's going on. So we'll be working a lot with function notation, and I just want to remind you that that is pronounced f of x, a of n, g of d, any variable that we would choose to pick, and the one in the parentheses is the input variable, what I am putting, a number into, and then the g of d or a of n would represent the output of the function. Okay, now 2 more words. These are used a lot in science, so I think as soon as you see them, you'll remember that these have been described a lot in science. So whatever this is most often x. It's the variable that provides the input of a function. And if you notice down here, most often y, or f of x, and that's the variable that provides the output of the function. 2 words. I'm going to give you a clue. There's an I and a D. 2 words. Okay, so the one that's the input is the independent variable, and the one that is the output is the dependent variable. And the way I like to think about it doesn't matter which function rule I go up to. I'll just take this one, for instance. This y is the dependent variable. He's waiting. He depends on what value you put in for x. The x is the independent variable. That's the one that's going to have the math done to it. And you can pick any value for x you want. We picked 5, but what if we had picked 7? 2 times 7 is 14, plus 4 is 18. See, the y is waiting. The output variable is waiting for you to finish doing the math. So usually we use in math an x as the independent variable. And usually in algebra, we would use the y or the f of x as the dependent variable. The dependent variable is by itself on one side of the equation. Okay, so today what our goal is to start writing function rules. And we're going to be given a table, and then I promise that we'll get to a place of like, where do I use this in a couple of minutes. So if we were to look at 5, 6, 7, 8, 9, those are the output. And if we look at 1, 2, 3, 4, 5, you can see the input. So if I input 1 into this function, 5 is going to come out. Same function machine, I'm going to put 2 into it, do some math, and 6 is going to come out, and so forth down the table. And what I'm trying to do is come up with a function rule like I saw on the other page. So let's just go back, like y equals 2x or f of x equals 2x plus 4. I'm trying to come up with this function rule given the table. So when I get back to looking at this table, how does this x relate to the y? When x goes in, what happens to make 5 come out? And my immediate thought would be, what about if I added 4? My second thought is, but wait a minute, what if I multiplied by 5? So those are my first 2 thoughts. So adding 4, could that possibly be what's happening to the input variable? Or is it multiplying by 5? Both of those work for this first entry. But let's go down. When 2 goes in, a different number enters this function rule that I'm trying to come up with. Does adding 4 work? Or does multiplying by 5 work? Well, 2 plus 4, cha-ching. But 2 times 5 is a eh. So right now, I'm really leaning on this plus 4. Does it work all the way down the table? So basically what I'm saying is forget the 5, right? I want to add 4. So I'm going to take my input variable, add 4 to get my output variable. And there would be my function rule. So y, my output, would be the input plus 4. Put in 1, add 4, you get 5. Put in 4, add 4, you get 8. And this function rule describes the entire table. Hey guys, this is an explicit rule. I can right now find out what would happen if x was 100. And if I put 100 in, I'll get 104. It's that same idea we were kind of talking about with explicit rules. Now, why did I use y and not f of x? Because that's what was given to me in the table. Let's try another one together. Okay, so here is a table. Notice this time we've changed the name on the output variable to f of x instead of y. It's just a different name, just like I could be called Mrs. W or I could be called Mrs. Woodruff. Mrs. Woodruff is more descriptive. It really points out who I am. Mrs. W, well, there could be a Mrs. Wilson somewhere, right? So that f of x is a little bit more descriptive. Now I've got a table, and 0 to 0, I have no idea. So I'm going to move down, and I'm going to say, I'm going to input 3, and I'm going to output 9. And I'm immediately thinking, well, what about adding 6? Oh, wait a minute. What about multiplying by 3? That might work too. So those are sort of my first two ideas, is to either add 6 or to multiply by 3. So I'm going to move down to the next row. And if I add 6, that would have been 12. So that doesn't work. And if I multiply by 3, 18, that doesn't work. Oh no. Is there another relationship to go from x to f of x? So now we're going to look, and you guys might remember from the last slide, or rather the last presentation, that these might be special. Do you see another relationship? What can you do to 3 to get to 9? What can you do to 6 to get to 36? Can you see it? How about squaring it? So these are all perfect squares. That's what kind of shouted at me. Maybe we need to think about that. So 3 squared, 6 squared, 9 squared, 10 squared. So notice that we needed to square there. So I'm going to take the input, I'm going to square it to get the output, and my function rule would look like that. Notice that we usually put the, you don't have to, but we usually put the dependent variable on the left. People just orient things that way usually. Okay, so what I'm going to ask you to do right now is to pause the video, and you can look at the first 4, but I'm really, right now, I would guess that everybody's going to be able to do 1 and 2 pretty easy. 3 is going to present a challenge, and 4 even more so. So pause the video, take a minute, take a look at these 4. I'm guessing 1 and 2, everybody's going to have. 3 might present a problem, and 4 is definitely a challenger. So pause the video, and when you've got your best efforts on all 4, play the video again, and we will join up. Okay, let's take a look at number 1. First of all, notice that there's an f of x there, so that should be in your rule. That's going to be f of x equals, and what do you do to the x to get the y? Did you get that you're adding 6? So if I put the 10 in for x, 10 plus 6, f of 10 would be 16. Notice we've got the y here, so you should have y in your rule. Ooh, got some negative works going on here. 1 plus -4, but 2 plus -4 won't work. But if I multiply by -3, did you get that? Let's stop for a second. Make sure you used y simply because that's what they gave you in the table. And you should be multiplying by -3. We do not use an x for multiplication. I know you know that. And notice I didn't put the dot in. It's the invisible multiplication dot. The other thing that is really important, I need you all to pay attention, very important algebra convention, the number when you're multiplying needs to go in front of the variable. So when you're writing multiplication, the number always goes in front. So if you had, for instance, y equals 2x, you would never write it y equals x2. So that number always goes in front. Now, before we move to the 2 tougher ones, does anybody remember what that number is called? The number that sits in front of the variable in multiplication begins with the letter C. It's called the coefficient. So the coefficient always goes in front in the multiplication. You must do that. Okay. All right, so this one got a little bit trickier. There, like adding 1, it was just, what is going on here? I can't see it going left to right. When that happens, you look for a pattern going down the outputs. So do you see something happening from -2 to 1? That's the same thing from 1 to 4, 4 to 7, and 7 to 10. And did you notice that the output, see that increase of 3? When that happens, you can't see it going left to right. You can simply write that number in front of the input. So you're going to take whatever this number is and multiply it by 3. Mrs. Woodruff, that's not working. You'd be right. Let's test it. If I put 2 in, 3 times 2 is 6, but I needed a 1. If I put the 3 in, 3 times 3 is 9, but I wanted a 4. And if I put the 4 in, I get 12, and I wanted a 7. Do you notice that you're always off by the same amount? You're always over by 5, so you need to subtract 5. This is a two-step rule. There's 2 operations involved. And that number that's going down, as long as these guys are 1 apart here, that number going down is the number that we are putting in front. We'll talk more about what that is in a future unit, okay? But now let's just test this. I'm not feeling very good about this one. Let's put the 4 in. 3 times 4 is 12. Take away 5 is 7. 3 times 5 is 15. Take away 5 is 10. And this rule does build this table. Okay, so the last one is the toughest. I don't know if you saw how to make this rule. We're going to start with a y equals. And adding 3 and adding 7 and multiplication doesn't work and going down isn't working. So this one was the toughest. That's what I would call a challenger. So when that happens, start thinking about things like cubing and squaring and, something like that. And if you had taken, usually I get, if I'm in class, 1 or 2 people actually get this, but if I had squared the 1, think about squaring the 2, squaring the 3, or doing cubes. So let's just try squaring. 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16. And if you notice, squaring, you're always off by 1. You're always too small by 1. So you square, whoops, sorry about that. You square and add 1. So let's try it. Let's put the 5 in. 5 squared is 25, add 1 is 26. And that's how you can make a function rule from a table. It can be an addition. It can be a multiplication. It could have been a subtraction, oh, by the way. If you're not seeing a pattern left to right, can you see the pattern going down and think of it? It's going to be a 2-step rule where you have to adjust. And then if that's not working, think about those special exponents as well. So where the heck does this get used, Mrs. Woodruff? So we're going to do a couple of really simple examples here, and that'll be the end of the video. We are going to talk about some big time conventions here that you will be held accountable, not just in a grading sense on quizzes and tests, but all the way through math. So I'm going to give you an example of a real model problem here that just got kind of cut off with the ice cream cone there. So let's just say that you're going to go into an ice cream store and it's $1.50 for every ice cream. We want to create a model. We want to create a function rule that will talk about, the total cost. So when we do that, no variables are ever given in the real world. Notice in the table here, there's no variables at the top. There are words. So you are going to come up with a variable that's going to represent the number of ice creams, and you're going to come up with a variable that represents the cost. And when you do that, you have to tell everybody, oh, by the way, Mrs. Woodruff too, what variable you picked. So you're going to notice over here, I'm going to use the little I for the number of ice creams. So this column would represent by the variable I, and I'm going to use C for that total cost. Now here comes another convention. I not only have to define my variables, but I also, if it has a unit like money, dollars, cents, if it has a length unit like meters, or time unit like seconds, you have to put your units in the definition. So basically what you're doing to everybody is saying, yo, everybody, I'm going to write a function rule. And when you look at that rule, when you look at that equation and you see an I, that stands for the number of ice creams. And when you see a C, that's the total cost. And we're talking about dollars, not euros, not yen, or some other foreign currency. So your variables have to be defined as to what they represent, and your units need to be in there. Now, when you go to write your equation, you will use the I and the C. You will not put the dollar sign in your equation. So one ice cream would be $1.50. Two ice creams would be 2 times $1.50, right? 3 and 4. And that's sort of the table that we're representing. So what would the rule be? Well, your total cost would equal the number of ice creams times $1.50. Very simple equation, right? There it is. But what you need to remember, no dollar sign in the equation, and the number has to go in front when multiplying. Don't put I and then 1.5 after it. So no units in the equation, but must be in the variable definition. If you have a final answer where you say, hey, we're going to buy 87 ice creams, and you take $1.50 times 87, then your answer would have the dollar sign in it, but not in the equation. And then don't forget that the variable follows that numeric coefficient. So one more example here. Let's define variables and write an equation to model the relationship in the table. This time, this is the number of candies, and this is the change from a $5 bill. You need to define variables, and you need to write an equation that will model this relationship. So pause the video and see if you can come up with it. Okay, let's see what you did. Now, your variables do not have to be mine, okay? But basically, I need a variable for the number of candies, and I need a variable for the change from the $5 bill. And I am going to use N for the number of candies. If you use C there, that's fine. And I'm using C for the change, and notice I put it's in dollars. Now, I need to write an equation here. So my change is going to be, now I have to figure out, I have $5 and I'm going to take away the cost of 5 candies. Think about that. My change will be, I'm going to hand $5 in, I'm going to get change back. So 5, and then take away the cost of the candies. The total cost equals 5 minus. Now, where did this 25 cents come from? Well, I had to do a little bit of intuition. That notice right here, $1.25 came off of that $5 bill. I lost $1.25, and there was 5 of them. Here, I lost $2.50, and there were 10 of them. So how much does each candy cost? 25 cents. I had to do a little bit of thinking there of how to get that. Does this work? Well, if we put the 10 in and we take 25 cents times 10, remember we want to multiply before we subtract, that would be $2.50. And 5 minus 250 would indeed give us 250. And you can test any of these inputs for N, and you would see you would get the outputs. Now, what I'm going to do on the next page is kind of baffle you a little bit when you look and say, Mrs. Woodruff, that's the same problem. It is, but I want to show you how it can change depending on how you define your variables. So I'm going to define my variables. Well, that looks the same, but no, it doesn't. Look what changed. So having the unit in there is important because now I'm not talking about dollars. I'm talking about cents. So when I go to write my equation, it's not going to be $5. It's going to be 500 cents. Minus not 0.25, but 25 cents. So again, your units is important because it actually can change how your function rule looks. So make sure that you put your units in your definition when you're writing your function rules. Just to remind you that these are the key words, like if you're having trouble and you see a word in a problem like quotient or each, or increased by. This is just a little chart that helps you remember, which words go with what operation. Usually these are a piece of cake for everybody, but sometimes people get a little confused with, especially the division words or some of the multiplication words, like, which one's product, which one's quotient. So that's just a little guide for you as we end our discussion today with a real world problem. So imagine that Staples charged $1.50 for an 11 by 14 glossy color copy. And we want to write a function rule to describe the relationship between the number of copies made and the total cost. We want to come up with an equation, a rule to show that. The first thing we need to do is figure out, first of all, in the problem, who's going to be kind of our X and our Y, who's going to be our input, who's going to be our output. So notice here that we've got copies made and total cost. So which one depends on the other? So which one would be your independent variable that would be your input variable? What do you decide when you walk into Staples? When you walk into Staples and you hand that picture to make a copy, you say to the person what? You ask them for a certain number of copies. So the number of copies is what you're deciding. That's going to be your independent variable. And the total cost depends on how many copies you make. Now, I need to pick a variable for the number of copies, and I need to pick a variable for the total cost, and I'm going to remember to put the $ in there. So these are my choice. You do not have to agree. You could have used X and Y, A and B, N and C, whatever, but I'm going to have C be the total number of copies, and T is going to be the total cost in dollars. My rule now has to have the T, the C, and the $1.50. So I'm going to take the number of copies, multiply it by $1.50, and that will give me the total cost. Right? So can you write the rule? It's an easy one. And it's really important that you make sure your variables are in the right spot. So your total cost will equal $1.50 times the number of copies. So if you were the final answer, if this was on a quiz, would be that you would need to define your variables, including the $. So right here, and you need to have that equation. So if you made 50 copies, you would take $1.50 times 50, and that would be your total cost. So today what we've been working on is kind of setting up some standards. And I just want to review those one more time before we call it a day here. So remember that when you're writing an expression or an equation, you must define your variables from a real world situation. So if it's a real world problem, you need to say what the variables you picked represent. Number two, when you're defining variables, your units, $, inches, meters, pounds, those kind of things have to be in your definitions, but they're not written in the equation. And then finally, in a term, make sure you always put the number in front of the variable when you're multiplying. That's called the coefficient. So today we are practicing writing function rules from tables and real-world problems, and we're starting full force in our algebra discussion. Guys, I hope you have a great day.